Alright, hi everybody. We are going to take a quick look, a reminder of how opened and closed air columns worked. We talked about this in class, but it can trip people up, some of the math, and we're going to do a little problem with it too. But just to remind you that this is a really important topic because a large number of instruments use these resonating air columns. They set up standing waves of air inside of them, and that is how they produce their sound. And we see these all the time. You can see it in a large pipe organ like this of all different length pipes, or xylophones, clarinets, and even the horns, where they take the pipes and they just wrap them around in these wild configurations. And clearly the length of the pipe has something to do with the sound that resonates in them. In fact, you see this definitely with the trombone as it lengthens itself. But even with all of these instruments, even something like a clarinet, when you put your fingers over the holes of a clarinet, you are effectively changing the length of that resonating air column. And if you remember, we looked at the formulas for how to deal with resonance in air columns. If you have a closed pipe, we are looking at integer multiples of quarter wavelengths, and you have to count these a little funny. You have to count 1, 3, 5. It's a little strange, but it's because the first frequency that fits in there has a quarter of its wave inside of the pipe for a closed pipe, and it increases accordingly. So you 1 quarter wavelengths, 3 quarter wavelengths, 5 quarter wavelengths, odd multiples, integer multiples, as you try to squeeze more and more of the of a frequency sound in there. Now with an open pipe, as you can see in the animation here, we're dealing with integer multiples of half wavelengths. The first frequency contains half the wavelength, and then you have 2 halves of the wavelength, or full wavelengths, and 3 halves of the wavelength, and so on. So we're going to use these formulas to try to answer what I think is more of a challenge problem. So if this makes sense, hopefully the whole unit will make sense to you. Here we have 2 air columns, and they're each 1.95 meters long, and one column is open and one is closed. And we want to figure out what the frequencies are that we can produce that are in the audible range between 20,000 hertz and 20 hertz and 20,000 hertz on a day when the temperature of the air is 12 degrees C. Okay, so let's see what we can come up with here. Now we're looking at an open column that's open at both ends, and a closed column that's closed at both ends, and we're looking for the lowest frequency, the second lowest, and then the highest frequency. We haven't really talked how you get the highest frequency that can work in there. Well, let's take a look. If I just begin by thinking about my I'm gonna go with blue. I like blue. So if I think about what the open air column is going to look like in this situation, if I draw a little one here, my first frequency that fits is going to be something that looks like this. I have to have an antinode at both ends because that's where a lot of the motion is happening. In the second case, I would have in this resonating tube, I still have to have the antinodes at both ends, but I can fit a full wavelength in here now, just like we were seeing from that PowerPoint slide, and so on. And we found that the governing formula for this is n lambda over 2, where n equals 1, 2, 3, and so on. So that is my governing equation for this. So the strategy I'm going to use here is I have a fixed length, 1.95 meters. I'm going to use that and this formula to find my wavelength, and then from that find my frequency, because I know V equals lambda F. Right? So let's take a look at that. If I use my L as 1.95 meters, and I say that is equal to, in the first case where n equals 1, it's just going to be equal to lambda over 2. That means my first wavelength frequency that can fit in there is going to be a wavelength of 3.9 meters. Okay, that's great. But now I'm going to have to use another formula, this one, to find what my frequency is. So, and just to demonstrate this, I'll write this in red. V equals lambda F, right? So that means if I want to know what the frequency is for a certain wavelength, I have to do frequency is V over lambda. So I have to use V. Oh, but wait a minute. They don't give me what the velocity of sound is at this place. They give me the temperature, but that's okay. That's okay because I can figure that out. If you remember back, we had a formula for the velocity of sound in air at a certain temperature, and it looks something like this. V equals 331 meters per second, which is how fast sound goes at 0 degrees C, times this kind of a little mathematical scaling factor, the square root of 1 plus the temperature of the air in degrees C over 273 degrees C. Now, if we do this in this situation, if you take 12 degrees, put it here, 12 degrees divided by 273 plus 1, take the square root of that, and multiply that by 331, you're going to get something a little bit bigger than 331. You're going to get 338.2 meters per second. So there's a secret little step in here that we had to use in order to get this. So let's see what we end up with now. Let's take this number and figure out what frequency that's going to mean we're dealing with in this situation. So this V is 338.2 and it's over this 3.9 meters, and so that's going to give me my fundamental frequency, my first frequency of 86.7 hertz. Okay, so I've addressed this first question here. The lowest frequency is the fundamental frequency. Now in this second case, let's try that. We got 1.95 meters. In this case, it's going to be equal to 2 lambda over 2. That gives me a lambda of 1.95 meters, right? Because 2 over 2 just cancels out. And now I got to find a frequency from that. Well, let's see. Frequency is the same thing. It's velocity over the wavelength. In this case, 338.2 over 1.95 meters. My second frequency that I can fit in this tube is one that is 173.4 hertz. And you notice both of these are within audible range between 20 and 20,000 hertz. But now this last question, so I got that. What about this guy, the highest frequency? How on earth are you going to figure that out? You just kind of trial and error until you get a frequency that is just under 20,000 hertz? Well, that's one way of doing it, but let's take a little stab at it. Let's say, okay, let's imagine if you have a frequency that's 20,000 hertz. Okay, what does that correspond to in terms of wavelength? Well, if you use the formula that lambda equals V over F, which is just this formula here, you'll find that that corresponds to a wavelength that is pretty tiny, 0.01691 meters, so says my calculator. Okay, that's great. Now, can that wavelength fit inside this tube in integer multiples? What I mean by that is, if I take the length of the tube, 1.95, and I set that equal to n times this wavelength, this number, and then divide that by 2, is my n going to be a whole number? Because it has to be. That's the requirement of this formula. And it turns out that when you do that, you get an n that is not a whole number. It's 230.63. N cannot equal 230.63, but n can equal 230. So just by checking the upper limit, I just figured out what n is going to need to be in order for this to work. So let's try an n of 230 and let's see what I get. So if I use 1.95 meters equals 230 lambda over 2, I get a wavelength that is equal to a similar number, 0.0169, what is that, 56 meters. And since frequency is V over lambda, that gives me a frequency of 19945 hertz. And lo and behold, look, that is within that 20,000 hertz limit. That is the problem is asking me about. So I just found the frequency, the highest frequency that will fit in that tube. Good for us. Now, basically, the problem says, hey, do it again. What about one that is closed at one end? Okay, so I can sketch that out for you again real quick too. Let's take a look at that. So Up here I did some sketches of those, so let's think about this in pictures first. Closed at one end is going to look like this. You have an antinode at the open end and a node at the closed end. This is my first frequency. My second frequency that's going to fit in here is going to have those same constraints, but it's a different waveform. Looks something like that. That's the second frequency. If I think, okay, I got a new formula now, and if you flip back in your notes, L now is n lambda over 4, where n equals 1, 3, 5. They're odd integers, which is a little strange, but that's all right. It'll work. All right, so let's see what happens now when I do this. I'm going to take my length of my column, 1.95 meters. That's the same in all cats. I'm going to give myself a little more room. 1.95 meters equals lambda over 4, because if n is 1, that just kind of goes away. That means my first wavelength is 7.8 meters. Different from what I had if it was an open tube, but my frequency, following the same pattern here, is v over lambda, which is 338.2 over 7.8, which gives me my fundamental frequency is 43.3 hertz, which was then the hearing range, so that works. Now if I do that over here, 1.95 equals 3 lambda over 4, because I got to skip the 2 and go right to the 3, then I get a lambda 2 of 2.6 meters and a frequency that is v over lambda, 338.2 over 2.6, and that gives me my next frequency of 130.1 hertz. Okay, now the only thing that's a little bit different in this scenario is, what about when I look at the highest frequency? What does that look like? Well, I can do the same trick again. If I say frequency is 20,000 hertz, what does that give me? If I solve for the wavelength, it turns out it gives me a number that is 0.01691 meters. And now if I try to plug that in to this formula, if I say 1.95 equals n times this number lambda right there divided by 4, I get excuse me, an n that is equal to 461.26. Now first of all, it's not an integer, so that won't work. So I need to basically round this to the nearest odd integer. In this case, I don't want to go up, I want to go down. 461. If I go up, I'll get a frequency, it turns out, that's beyond 20,000 hertz. I don't want that, so I'm going to go to 461 and let's see what happens. 1.95 meter tube equals, now it's 461 times lambda over 4. That gives me a lambda of 0.1692 meters, which corresponds to a frequency of 19990 hertz, just barely within that 20,000 hertz audible range. So there you go. So that is how you want to approach these kind of problems. This one was a little more involved, but I think just by looking at all the details, it can help make sense of all of that. So